that equal to 1. X is greater than or equal to 0, less than y over 2. And z is between half and 1. And this problem is very, very nice. I still remember it, okay? So now remember that the surface integration, I will use 1 plus partial f partial x, partial f partial y, and let's see. The surface is a part of unit sphere, because I'm giving you a sphere here, which is x squared, y squared, z squared. Of course, you are not going to know this unless you, as I told you, make a revision of the various surfaces. Okay, and here is the trick. X is greater than or equal to 0, less than or equal to y over 2, so it's a part of the circle. I'm sorry, this is sphere. And the z also, you have two planes, half and 1. So that's the surface that we want to go through. I don't have the function z expressed as a scalar value or as a function in x and y. I believe going through this direction or the other one as we talked previously. Let's do parameterization, and once, because we are dealing with a spherical domain or a spherical surface, so it will be a very good idea to use spherical coordinates. But once you go through spherical coordinates, it means you will parameterize your equation. Once you parameterize your equation, I will leave this guy and I will work with the area of RU cross RV. This problem is really very important. I want you to go through it more than once, step by step. So now I have x, which is sine phi cosine theta, y sine phi sine theta, and z is cosine phi. Of course, the r is equal to 1 since we are talking about a unit sphere. It's here, x, y squared, z squared equal to 1, so r squared equal to 1, so r is equal to 1. So r here is 1, r here is 1, r here is 1. So I'm parameterizing, instead of having u and v, I'm talking with phi and theta. Remember. And of course we know the Jacobian in the case of the spherical coordinates. The spherical coordinates should remember this. And now once more, the ds, which is rho phi rho theta, d phi d theta, is going to be sine phi d phi d theta. So I will have this on the side. Now all I have to do is to just integrate on a double integration, since z is equal to 1, so sine phi d theta on the domain which is d, as you can see from this objects. The trick here is to identify the value of phi and the value of theta. And in this case, I will need to visualize what I'm going to do. So first of all, let's remember, that's the equation of the unit sphere. X squared, y squared, z squared equal to 1. And that's the relation connecting x and y. X is equal to, or less than or equal to y over 2. So I'm talking about this area. This is the x-axis, that's the y-axis. This is the area I'm talking about. We are in 3D, so I didn't mention the z. So I'm talking about this slice here from x and y going up. So that's the shape, it's the surface, it is the sphere, and we have this prism going up, as you can see. Okay, and for the z between half and 1, that's the part that we are talking or interested in. The sphere, the prism intersection, and the plane, as you can see. You will have to understand all of this, or this has to be understandable for you. Now I will come to the boundaries, to determine the boundaries. The first of them is z, greater than or equal to half, less than or equal to 1. I know what's z in spherical coordinates. Z in spherical coordinates is r cosine phi. R cosine phi. R is equal to 1. Which means I will have cosine phi equal to half or cosine phi equal to 1. If I have cosine phi equal to half, then I can do cosine minus 1 and getting the values of phi, because I need them in this integration. It's going to be a function in phi and theta. So I need to identify this. Okay, so cosine phi, it will equal to half. I need to find the function, the angle. And cosine phi is equal to 1. what's going to be the argument? So cosine minus 1 of 1, which leads to 0, because the value of the cosine will equal to 1 at 0. And cosine minus 1 at 5 or 0.5 is going to be 60, which is pi over 3, okay, radian coordinates. So 5 is going to be cosine minus 1 over 1, cosine minus 1 over 0.5. This is how I determined the values of the phi. If you remember in spherical coordinates, the phi is going from the positive z direction to the r or the unit. So now I've succeeded in determining the values of phi. That will help me to identify the values of d equal to half and 1. And this is why phi will be running from 0 to pi over 3. 0 because it is the cosine minus 1 of 1. Pi over 3 because it is the inverse cosine or the arc cosine 4.5. Now going to the values of x is greater than 0, less than y over 2. Now I am in the pi 1, which is the relation between x and y. X is less than or equal to y over 2. Let's make the substitution using spherical coordinates. So this is going to be sine phi cosine theta. That's going to be sine phi sine theta. So trying to get them all together, cancelling cosine phi, sine phi and sine phi, and dividing on sine theta. So I will have cot theta equal to half cosine over sine, which is cotan theta equal less than or equal to half. That's theta less than or equal greater than or equal cot minus 1 half, because you make an inverse for both sides. Now I will need, it's really very simple, cot half, it's going to be, you have your calculator and you can evaluate it. It's going to be equal to 1.0107 plus pi over 2. So now I've determined the relation. Sine phi, d phi, will run from 0 to pi over 3. This is going to run from 1.107, which is the inverse cot for half. And also I have cot minus 1 plus a pi, which is 3.14. So I will have the limits here and I can integrate these double integration, very, very simple. This is going to be sine phi, so it's going to be a negative cosine of a phi, then replacing cosine phi by y over 3 and 0. Then integrating with respect to the theta, I will get the value as you will see. Going to problem number 3, he's asking you about the surface integration. Stop! He's giving you vector fields. So now, if you are integrating on the surface, you have the vector field. Now I get the feeling that I will be using the other formulas that will help me with the vector field, which is the flux formula, or using the divergence in use. Let's go through each part of these guys. The first problem is calculating the following surface integral of a vector field. Just a second, I'll check the time, please. Okay, we are very good. So, all I have to do now is to calculate the surface integral of this vector field. Here's your vector field, F, and the paraboloid with the equation. Of course, it doesn't have to do this, because from the equation I can know the dimension of the surface. Located blue x above, x0 y plane, and in the normal direction. So now I will use the divergence theory, as you can see, in order to evaluate the value of this surface integral of this vector field. Okay, it's really very simple. What I have to do is to get f dot n with the direction surface integration that can be easily replaced with the triple integration with the diversion of the vector field. Okay, the vector field is okay, it's already here. H is y minus x plus 8 of k. So getting the divergence is not going to be a problem, because the divergence, simply, if you remember, I will get partial f1 partial x plus partial f2 partial y plus partial f3 partial z. That's gonna be the dive of this vector field, which is really, very simple. The game now is to identify the domain. So the region that we are talking about is about of a surface of a paraboloid, which seems like a paraboloid. If you move 9 over e, it's going to be z minus 9 to the vertex at 9 on the z, and it's looking downward. So I believe that's the shape of your paraboloid. I need to evaluate the area above OXY or above pi 1. So I'm talking about this guy. I'm talking about this part. And of course, I will need to identify the intersection, which is very, very simple. Just inserting z equal to 0 in this equation here, and I will have x squared y squared equal to 9. That's the disk that I'm going to deal with. Okay, once more, I will get the normal vector. So f dot m ds, that's going to be the divergence, but instead of dealing with the surface integration, I will be dealing with this triple integration, which is very, very simple. Okay, f dot ms, that's the f function, and getting the diversion of this function is going to be really very easy. That's the f function component. I'm preparing to get the n vector, which is going to be the derivative with respect to x, with respect to y, with respect to z. That's the n vector. So these are the components that I'm using for this guy. Now I have also the f function is given to me. That's the f function. All I have to do is to make the multiplication. So I'm multiplying y times 2x, negative x times 2y, and the 8 times 1, as you can see. I have the integrand. I will start doing the triple integration. Of course, what's going to be a very friend for me now to go through this triple integration, which is going to be f dot n with respect to the s. I have z here. I'm talking about the this z component. So it can be replaced by this disk. So it's just only the integration of a dx dy. Area of a disk, you can just integrate through replacing this into r d theta, as we did go through. The radius will be from 0 up to 3. The angle is from 0 to 2 pi, or just use the area of a disk, which is pi r square, and you will have your thing. For the second problem, it's also the same second problem in this part, which also will be exactly the same steps. All I have to do, I have f. I will need to get the n vector. That's the equation of a paraboloid also. And, this is really very nice, because he is giving you the intersection for the region between a paraboloid and the x equal to 1 minus y squared, x equal to y squared minus 1. That's a part of a parabolic cylinder, and that's another part of a parabolic cylinder. So that's the paraboloid that we are talking about. Z is equal to x squared y squared. That's the intersection between the paraboloid and the equation of x, 1 minus y squared. And that's the other guy from the other direction. This is actually the part was y squared minus 1 for this one. And that's for x minus y squared. It will go on this side. So once more, to imagine the surfaces that we are dealing with, these are 1 minus y squared and y squared minus 1. So that's x equal to 1 minus y squared, x equal to y squared minus 1. If we move the camera upward, this is going to be the shape, and all of this with the intersection of the paraboloid. So that's the shape that we are talking about. And that's also the shape from above. That's the paraboloid, and these are the two parabolic cylinders. The shape is very good, it's very nice. And also I sent you the PDF to be with you, just to go through it. The catch here is not going to be the main integration or the main steps. The catch will be within the boundaries, as you will see. So now once more, I have f, which is x minus 1 and 2x squared. I will have to run for the region. Here's x y squared minus 1 to the left, and xy minus y squared to the right. I will change the surface integration by the divergence into 3D. So I'm getting f dot n, which is really very simple. That's the f function. I have it. and z is equal to x squared y squared. So in all direction, in order to get the n vector, which is going to be z minus x squared minus y squared, differentiating, which is going to be lead to negative 2x, negative 2y, and 1. Here we go, that's the n, which is the gradient of f. I will now get the f function, which is also very, very simple. Of course, here we have orientation directed downward. This is why the n, I will multiply it by n to get the negative direction. So it's going to be 2x, 2y minus 1. And I will do f dot n. So I'm multiplying the n times f. I'm working with the main formula here. So multiplying both of them together. Now I will have the multiplication which come up to negative 2y. All of this is straightforward, just direct substitutions. The catch here is to determine your region or the domain, which is actually located between these two guides, x, y squared minus 1, x, 1 minus y squared. If you look deeply between these two parabolic cylinders and look to their intersection in OXY plan, you will have this shape. So x here is the region between 1 minus y squared and the greater than y squared minus 1. And that's the shape that we are talking about. That's a parabola, that's the other parabola, and we need to determine this guys. So if I consider x equal to 0, y equal to 0 to get the intersection at the x-axis. So at y equal to 0, when y equal to 0, I'm talking about this line here. So I will have here negative 1, and the extension here for the x direction is going to be positive 1. So x actually will run from negative 1 to positive 1. And if we go to x equal to 0, or to the two inequalities, 1 minus y squared is greater than y squared minus 1, moving y to one side and the numbers to the other sides, I will have 2y squared less than or equal to 2, which means y squared less than or equal to 1. That's y is less than or equal to 1 and greater than or equal to negative 1, as you can see. Here is x belongs to negative 1 and 1, y belongs to negative 1 and 1. Now I've determined the region exactly. I know the region now. So we will be able to go through our domain integration, which is going to be integration from negative 1 to positive 1 for y squared minus 1 into 1 minus y squared, just the multiplication negative 2y, as you can see. It will be very simple. I will integrate first with respect to dx, then making the replacement of x 1 minus y squared minus y squared minus 1, then I will do the dy integration. And it's really very simple. For problem number C, he is giving you f as 2x plus 1, and it is located on the spherical surface with the equation x squared y squared plus z squared equal to 1, and between the plans z equal to 1 and z equal to negative half. That's also a very interesting problem. Okay, the spherical surface here with the equation, as I told you, that's our sphere. That's the plan at z equal to 1, which is going to be by the end of the sphere. The problem will arise with z equal to negative half. So I'm talking about this part is going to be neglected. I'm talking about this part of this sphere, which from z equal to negative half to the full sphere or to the whole sphere. So if I want to signify this for you or to give more clarification, that's z equal to negative half. So I'm talking about this guy here, all of this part, okay, without the upper part. So that's the case that we are dealing with. Once more, exactly like the previous problems, as you will see, f and s, if I wanted to go through the triple integration, remark, if we go for the triple integration, that's f dot, the divergence of f, I'm sorry. So I will have, all of these are zeros. I will have just only this guy also equal to 0. So the integration with the volume, with the triple integration, I will be integrating for an integrand equal to 0, so the result will be 0 directly. So this means if sigma is a closed surface, then the total flux is 0. But our surface is not closed. Actually, the geometric case reflects that it's not closed. As sigma is the spherical, as I pointed out, kept between z minus half and z equal to 1. Missing the bottom disk, and this is what I've tried to take. So I would break it into two parts, as you will see. I will take sigma 1 for the spherical cap curved part, which is the part above OXY, or the curved part of all of it, and sigma 2, the disk at z equal to negative half. Identifying the z equal negative half, all I have to do is to replace z by negative half. It's going to be a quarter, so I can get the value of this disk exactly as you will see. The surface overall will be the union of sigma 1 plus sigma 2, or the sum of both of them. And that's what we have, sigma 1, sigma 2. As long as it is equal to 0, it means these two guys equal to 0, the sum of them, which means one of them is equal to the negative of the other. So I will use my knowledge just to evaluate sigma 1 or sigma 2, and this how I will be able to determine the flux on this part. This is what's going to happen now. This is sigma 1, sigma 2, as I told you. And here we go. This is the end of the previous slide. That's F, which is 2x plus 1 in the direction of K. Compute F dot N, so I will need to identify Z at Z equal to half, what's gonna be. Z equal to negative half, I will make the substitution. So it's gonna be x squared y squared plus negative half to the power of 2. That's x squared y squared equal to a 3/4. Now I have the radius of this equation, or of this disk, which is root 3 over 2. Direct substitution, getting the F as we already have, and making the dot multiplication of L dot N. I will have negative 2x minus 1. Then I will integrate on the disk at 3 over 4, as you will see, integrating with respect to x with respect to dy. Some problems you will find the trick is in the domain or in the range, or in the worst case like this problem, to identify the suitable surface to be able to evaluate your value at. The flux here is going to be negative 3 pi over 4 for sigma 2, and for sigma 1 is going to be 3 pi over 4. This is why the summation of both of them equal to 0. Problem number 6 also is very, very nice problem, and going the same way. Here he wants you to get the tangent line and to consider the vector field. He's giving you a vector field. He wants you to evaluate the integration on the contour. Then consider a vector field given by this function, and that's the surface of also a paraboloid with z greater than or equal to 1. And he wants you to evaluate the surface integration. This is really a very simple problem. I will go through it rapidly because the time is ticking. So first of all, I'm talking about an ellipse, so I can parameterize it. As I told you, it's very important to parameterize, to go through parameterization. So it's going to be cosine t times 2 y is 3 sine t, and z equal to 1. But the main issue is to determine actually the value of t within these boundaries. So I have 2 cosine t equal to root 3, and from here I will be able to get the value of t, and also I can get the value of, to check the value at y, it should be the same. So once more, that's the point that I need this straight line at. So I will put root 3 equal to 2 cosine t, which will leave me with cosine t equal root 3 over 2, that's t equal to pi over 6. Exactly in a similar manner, I'm just checking the y because I have just only one t. So if y is equal to 3 over 2, same way like t will equal to pi over 6, so it is now I'm sure. Okay, differentiate the parameterization. I will get r of t, which is 2 cosine t, 3 sine t, and 1. Differentiating to get r dash, which is going to be negative 2 sine t, 3 cosine t, and 0. And then I will insert at t bar equal to 6. This is the value of my r dash. Now I am ready to write this parametric form, which is going to be really very simple. The equation of the tangent line. I will have the point, which is root 3, 3 and 2 and 1, and s, which is the parameterization variable, times the vector in the direction of this straight line, which is given by negative 1 root 3, 3 root 3 over 2, and c. For the second part, you want you to evaluate the contour integration, given the phi is defined, and you have your r relative to the surface, the equation that's given by x squared over 4 plus y squared over 9 equal to 1, which is actually a cylinder. So now we will have the same parameterization since the cross section is the same. So as you can see, this is x, y, and z equal to 1. So z cubed is gonna equal to 1 also. Now I can find all what's missing here. This is the phi direction, which is y, z cubed, x, y, parameterized by this relation. So it's gonna come up to 3 sine t1 plus 6 cosine t sine t. I have r dash, which is the derivative of this formula from r. Now making the dot product of f dot dr and integrating on the contour of this function, which is going to be from 0 to 2 pi for these values of t, which is going to be really very simple and the direct relation for the integration. It's going to equal to negative 6 pi. The last part in this problem, number 6, is giving you a vector field, is giving you sigma, which is, as you can see, a part of a paraboloid, and he needs z is greater than or equal to 1. So that's z at 1. I'm looking about this cap. If you make the substitution of z equal to 1, you will have exactly the ellipse equation that we were handling previously. It's going to be x squared over 4, y squared over 9 equal to 1. So this is why I'm using the same relation, and I will evaluate the surface integration using Stokes' theorem. So I will need to get the curve of gradient times f, and I will do the contour integration, as you will see. F is given by this function, and notice that the curve is the same as in B in the previous, as we saw it's x squared over 4, y squared over 9. So just simply making the parameterization, and I will have r of t ready now to get dr, which is going to be the same. That's the f function. Multiply both together, both of them together. Now I'm ready to integrate on the contour, which is going to be from 0 to 2 pi, exactly the same as you can see, from 0 to 2 pi to the result of the multiplication of f. I've already solved for you the problems, number 8, number 9, number 10, all solved, and I will go through it later with you. For the time being, I will send you all these solutions. It's really very direct, very simple, either using, as I told you, to determine the flux or the flow of the vector field, or to identify the divergence using divergence theory. So it's direct substitutions. Here he needs you to determine the flux of a vector field through the surface S and the boundary of the solid given by x squared, y squared less than or equal to 1, y is less than or equal to 0, and z is between 0 and 1. Going directly to Stokes' theory, that's the vector fields that I have. That's the region are given by a cylinder, and then between z equal to 0 and z equal to 1, I'm talking about this part. It's very, very simple to determine and to identify the disk, which is going to be x squared, y squared less than or equal to 1. This is the upper half of the cylinder, as we explained. Getting the gradient vector in order to be able to get the divergence. So differentiating f with respect to x, with respect to y, with respect to z. That will leave me with x, z plus x plus y. I will do the triple integration. Of course, cylindrical coordinates will be very good idea here in order to handle this triple integration, where dv is rdr is actually dz dr d theta, or dz dr d theta, as we know. The z is going to be from 0 to 1, and for r and theta, it will be from 0 to 1 and 0 to pi, in order to identify the relation, the limits of the integration. That's x, y, and z. I will make the substitution. It's an r dz dr d theta, and that's the integration from 0 to 1, 0 to 1, 0 to pi. I've used half of my cylinder because I'm dealing with y only greater than or equal to 0. If I don't have this guy here, then the integration will be from 0 up to 2 pi. It's a direct triple integration. I will integrate first for dz. So I will have, this is going to be z, this is going to be z, which is going to be 1. This is going to be r times z squared over 2, so it's going to be half of r. Then I will perform the r integration, and finally the outer integration with respect to the z. And you will have your flux here. In a similar manner, he is giving you, consider the vector field phi, is identified. Verify that the vector field is conservative. Stop. How to identify a vector field is conservative? In order to do so, remember, within the green, partial q, partial x equal to partial b, partial y. And this is actually what I'm going to check here. Partial f1, partial y, partial f2, partial f1, partial x equal, once more, partial f1, partial y equal partial f2, partial x. This is x, not y. This is x. So, and you will see this typo. Partial f1, partial y is going to be 2xy plus x. Partial f2, as I told you, partial x. So this guy is x. You will have them equal to each other, which means the field is conservative. Getting the potential function is very, very simple. All I have to do is to integrate twice. I will integrate the f1 with respect to dx, then I will get a constant in y. I will do the same and compare them. Here we go. This is f1. That's the first component with respect to the x. I will add a function in y. Similar manner, this is f2. I will integrate with respect to dy. I will add a function in x. Then I will compare them together. These components are the same. I will take y squared and a constant, and that's the potential function. Problem number 10 is asking you to perform this triple integration, and he wants you to evaluate the flux. It's going to be really very simple, and as I told you, I already solved it for you, and I've attached this solution also on the PDF, so that's the solution of this problem. Thank you very much. I'm sorry that I don't have extra time or more time for this session. We will do a revision soon, inshallah, on everything that we had from the beginning of our course till the end of our course. Also, I will try to solve one of the previous exams with you step by step, just to make you go into the mood of having an exam and solving each part of it. We will do this, inshallah, within the next session. I thank you very, very much, and I would like to tell you that you need extra hard work. Use the coming days in a very good way. Good time management. Go between going out and studying. Don't lose your attention within the coming vacation. I wish you the best as always, and with my best wishes, inshallah, I'll see you next time. Bye-bye. Thank you.